Hello my dear students, let's start the another part of general organic chemistry, that is GOC. So yesterday I have already discussed about carbocations, carbanions and free radicals. So let's see the reactions which may come in your forthcoming entrance exam on the intermediate. So this is the reaction, okay, this is the main reaction. Product is not mentioned, you have to write the product. Which is the product? So think it, which is the product formed here. So the most probability is this, because this is alkyl halide and we know that alkyl halide easily undergoes nucleophilic substitution reaction. So this is the most probable reaction, but in entrance, remember it, in most of the cases directly it is not given. So there are some reactions for which you need to know the actual mechanism of the reaction, then you get the answer. So answer is, see it, CH3 CH3H CH2Br. In this medium, as bromine is more electronegative than carbon, so bromine releases by taking electron from carbon. So bromide ion is eliminated and you get a carbocation, and the carbocation is primary carbocation. You know that if the carbon possesses positive charge containing CH2 primary, CH positive secondary, C positive tertiary. One of the most important feature of carbocation is that it undergoes rearrangement to form more stable carbocation, okay, it undergoes rearrangement to form more stable carbocation. Now that's why this is a primary carbocation, and you know that primary carbocation is the least stable, very less stable. That's why it undergoes rearrangement. It undergoes rearrangement. This is called 1,2. Hydrogen takes the electron also, bonding electron. So it is 1,2 hydride shift. This is also a part of entrance question. Okay, what type of shift is there? So CH3 CH3, and as carbon loses its own electron, so carbon becomes positive charge. So it is CH3. Now this is a stronger nucleophile than bromide. This is a stronger nucleophile than bromide. So this nucleophile gets attached here. It is a 3-degree carbocation, and you know that 3-degree carbocation is more stable than primary or secondary, okay. That's why by rearrangement you get tertiary carbocation. So the final product will get CH3 CH3O CH3. This is the final product. So the correct answer is option D is the correct answer, okay. So option D, I think you understand it, clear. Now the next question. See the next question. Bromide releases because it is more electronegative than carbon, but it releases under this reacting condition. So you get primary carbocation. As you know that if we consider all the 3 carbocations, the least stable carbocation is primary. That's why it undergoes rearrangement and the hydrogen takes up the electron from carbon. So hydrogen releases at H negative ion. That's why it is called 1,2 hydride shift. and you get tertiary carbocation which is more stable than primary, and as it is a strong nucleophile, so it gets attached to the carbon, so we get the final product here. Okay, we get the final product here. Now do the second question, do the second one. Clear? I think you understand it. These are all very important type of question in your exam. So if you consider medical, that is NEET entrance, then in most of the cases you get direct question from NCERT. But if you consider JEE mains, okay, NCERT based questions are come, but there are certain tricky questions also. So this is a type of tricky question. What is the product form here? Okay, I have not given here option. Clear? What is the product formed here? This type of reaction is called ring expansion. This type of reaction is called ring expansion. Okay, this type of reaction is called ring expansion. So let's see the answer. Obviously you get the option, but due to less space, less time, I am not giving any option here. Okay, so see it. Actually in my last classes I have discussed about pinacolon rearrangement. This is also an application of pinacolon rearrangement. These rings are symmetrical, both are symmetrical because they are tetrahedral cyclodene. That's why the hydrogen positive ion, that is proton, gets attached to any of the oxygen atom. Okay, and thus you get OH here, OH2 positive. It's a similar type of rearrangement like pinacolon. As oxygen is more electronegative than carbon, in everywhere there is carbon. Okay, so oxygen attracts the bonding electron from carbon. So you get the product OH. The carbon possesses positive charge by losing one water molecule. As oxygen is more electronegative than carbon, so oxygen cannot have positive charge. This is carbocation formed. Now what happens? This bond, see, this bond shifts here. Imagine it, this is the bond. The bond is attached with this carbon atom. Just shift in this way. So actually this carbon loses its own electron. So you get here this carbon loses its own electron. Okay, this carbon loses its own electron. So here you get the carbon becomes positive charge. Remember it, this releases as this way. As carbon cannot have positive charge, because this is a carbocation is not the product, so that's why this bond shifts here, and you get the final product. Here 5 bonded. Listen now, 1 2 3, 4, 5. 5 bonded, okay? This is the 5 bonded. 1, 2, 3, 4, 5. And here double bond is there. That is keto group is formed. This is called ring expansion. This is 4-member ring. This is 5-member ring. This is 4-member ring. This is 5-member ring. Listen now. This is symmetrical glycol. It's a type of glycol, okay? It's a type of glycol or a type of pinnacle. Symmetrical. In case of symmetrical, the carbon where carbocation is formed, the ring expand from other sides. The carbon where carbocation is formed, the ring expands from other sides. Ring expands from other sides. This is a symmetrical. That's why you can add H in both of the cases. But if the rings are unsymmetrical, then listen. Always more ring type cyclo compound is formed, okay? Remember it, 5 or 6-membered rings are more stable than 4-member rings, okay? 5 or 6-member rings are more stable than 4-member rings. So I think you understand it. This type of reactions are called ring expansion. This is the main product. 5-membered, 1, 2, 3, 4, 5. 5-membered ring is formed, okay? So let's see another reaction that's also type of ring expansion but in unsymmetrical cyclo rings. See it. If you consider this compound, then question is that the hydrogen atom, that's the proton, is attached here or here. See the technique, listen the technique. The hydrogen ion is attached to smaller ring OH group. So remember it, the hydrogen positive ion is attached to smaller member. This is the 5-membered ring, this is 4-member ring, the smaller member OH group, okay? The hydrogen atom is attached to H positive ion. This is the technique, is attached to the smaller membered ring. That's why this hydrogen positive attached here, because oxygen has lone pair of electron. So you get now, as oxygen is more electronegative than carbon, so oxygen cannot have positive charge. That's why oxygen attracts the bonding electron from carbon. So water is eliminated here. As the carbon releases its own electron, the carbon becomes positive charge, okay? So the carbon becomes positive charge. So listen the technique. If both the ring contains same member lines, then you can attach hydrogen positive ion at any of the OH group. But if there are unsymmetrical cyclogroups, this is 4-membered cycloring, this is 5-membered. So remember it, the H positive ion always gets attached to the smaller membered ring. I have already mentioned here. Now this ring, this bond shifts here, just like this, just like this. So you will get like this. This bond remains like same way OH. So here you get this type of bond, 1-membered, 2, 3, 4, 5, 6-membered. It has 5-membered ring, 1, 2, 3, 4, 5. You will get here 1, 2, 3, 4, 5 and 6-membered rings. And the carbon becomes positive charge here because the ring shifts from here, just here. Now the bond shifts here, and the final product you get, this is a 6-member, 1, 2, 3, 4, 5, 6, 6-membered ring. And listen, adjacent to their double carbon. This is the main product. This is the main product. So this type of reactions are called ring expansion. Understand it. If the two rings contains symmetrical cyclogroups, you can attach the hydrogen positive ion at any of the OH group. In the previous question I have already discussed. But if there are unsymmetrical type of cyclorings, it has 4-membered, it has 5-membered, the hydrogen positive ion always gets attached to that OH group which is attached to the smaller membered ring. This way you get it. Remember this, okay? If it has 5-membered, you get 6-membered. If it is 4-membered, 5-membered you get, okay? Remember it, 5-membered and 6-membered rings are very stable, okay? Are very stable. I think you understand it. Now see the next question. Remember it, if during any reaction carbocation is formed as intermediate, it has a tendency to rearrange itself to get more stable product. And you know that tertiary carbocation is more stable than secondary, secondary is more stable than primary, okay? Now you have already know the ortho para directing group. So let's check ortho para directing group and the conception behind ortho para directing group. This is benzene. These are notes, okay? This is a notes. I have seen questions from here also, okay? This is benzene. Already say halogen, chlorine, bromine or iodine, not fluorine, okay? Chlorine, bromine and iodine halogens are attached here. Now, if you want to introduce any atom or group on benzene ring. Say whenever this is chlorobenzene, you know that this is chlorobenzene. When treated with chlorine in presence of ferric chloride, the reaction is called chlorination. And during chlorination, Cl atom is introduced on the ring. This carbon is already occupied. So the Cl atom, which is attached to the rest of the carbon atom of the ring, is attached at ortho and para positions. Is attached at ortho and para position. You know that when there is already one substituent, then the next position is called ortho, meta and para. From here also ortho, meta and para. So the incoming Cl atom goes at ortho position and para position separately. Incoming Cl atom goes at ortho and para position separately. In most of the cases, ortho product is minor and para product is major. This is ortho dichlorobenzene and it is para dichlorobenzene. Remember it, in most of the cases para is the major because due to the closeness of two atoms or group, there is some steric repulsion takes place, and due to this steric repulsion the ortho product becomes minor. Here, as they are far from each other, that's the major. But one very important question is there are some compounds where ortho is the major. Next question I will discuss. Let's understand the topics. Why we get the incoming group at ortho and para positions? This is resonance. So remember it, by resonance negative charge density increases at ortho and para position. So the incoming electrophile, one thing is, remember it, whenever any atom or group is introduced on benzene, it carries positive charge or it has shortage of electrons from octet. They are called electrophiles. Next portion I will discuss electrophilic substitution reaction. Incoming electrophile is attached to the ortho and para positions. That's why we get ortho and para product. Such type of groups are called ortho para directing groups. Such type of groups are called ortho para directing groups. So remember it, any ortho para directing groups if present on benzene. What are ortho para directing groups? How to know? I will discuss now. Okay. At first, understand it. Any ortho para directing group is already attached to benzene. The incoming electrophile. What are electrophile? I am discussing. Okay. The incoming electrophile is attached at ortho and para position. In most of the cases, para is the major and ortho is the minor. Due to steric repulsion, it becomes less stable. So, I think you understand orthopara directing groups. Now halogens and amino group, hydroxy group, substituted amino groups, all are examples of orthopara directing group. How do you know what are orthopara directing group? Listen one technique. Listen one technique. How do we know what are orthopara directing groups? If you consider this, or if you consider this compound, or if you consider this compound, see, the atom which is attached to the ring, if contains only sigma or single bonds in both of the sides, then it has orthopara directing nature. If any atom of the functional group which is attached by sigma bond on both sides, any sides, it has orthopara directing natures. So remember it, if any atom or group which is attached to the ring has sigma bonds, it has orthopara directing natures. Clear? If any atom attached to the ring contains only sigma or single bond, it has orthopara directing nature. Most of the orthopara directing groups, when attached to the ring, they donate electron to the ring. So the negative charge density at ortho and para position increases. So the negative charge density at ortho and para position increases on the ring. That's why this type of group activates the ring. This type of group, they activate the benzene ring. Why they activate the benzene ring? Because due to resonance, they lose electron to the ring, and due to resonance, negative charge density increases at the ortho and para position of the ring. These are ortho position, this is para, I have already mentioned. That's why the ring is activated. The ring is activated, that is, the reactivity of the ring increases. That is, the reactivity of the ring increases. So they increase the reactivity of the ring. Clear? They increase the reactivity of the ring. They increase the reactivity of the ring. But if you consider halogens, if you consider the halogens when attached to the benzene ring, if you consider the halogens when attached to the benzene ring, see, the halogen is attached with the carbon of the ring. Here is carbon of the ring. As the halogens are more electronegative than the carbon, so the halogens attract electron little bit from the ring also. Actually, in orthopara directing cases, due to resonance, benzene attracts the electron. Here, the ring attracts 100% of the electron from these groups. 100%. That's why the negative charge density at ortho and para position increases completely. But if you consider the aryl halides, that is when the halogens are attached, then little bit they also attract electron from the ring, little bit. Say if here they attract electron 100%, they attract electron, here say 80%, the ring can attract electron 80% and the rest 20% the halogens attracts. That's why they deactivate the ring. They deactivate the ring. Okay, that's they deactivate the ring. That is the reactivity of the ring decreases with a little extent. So these are about orthopara directing group. I think you understand it. Clear? These are about orthopara directing group. I think you understand it. The main thing is resonance. I will discuss, okay, in this chapter. Now, what are meta directing groups? What are meta directing groups? Remember it. Orthopara directing group, when attached to the benzene ring, the atom carries single or sigma bond. But when you consider meta directing groups, the atom or group directly carry multiple bonds, okay, pi bonds. If you consider nitrobenzene, this is nitrobenzene. Actually, if you draw the structure of nitrobenzene, see the nitrogen atom which is attached to the benzene ring is further attached with the pi bonds. You know that double and triple bonds are considered as pi bonds. That's why this group attracts electron from the ring. This group attracts electrons. So remember it, all the meta directing group attracts electron from the ring because the atom of the group is attached by pi bonds. Pi matlab double or triple. That's why the electron density on the ring decreases. So at ortho and para position, positive charge is developed. The electron density on the ring decreases. So if we consider ortho, para and meta positions, these are ortho, para, these are meta positions. If you consider ortho, para and meta position, see, ortho position has positive charge, para position has also positive charge, indicates that there is a shortage of electrons. But if you consider the meta position, there is no positive charge. So comparing ortho, meta and para, meta position is more electronegative than ortho and para. That's why the incoming electrophile, okay, this is incoming electrophile. Whenever you want to attach or introduced any atom or group on the ring, they are called incoming electrophile. In the next class I will discuss, okay, regarding electrophile, attacking reagent, electrophilic substitution reactions. So it's get here, and thus you get the final product. This, that is meta product. So remember it, when meta directing groups are present, then the electron density on the ring decreases at ortho and para positions. So meta position is more electron cloud resulting the incoming electrophile is attached to the meta position only, and we get meta product. That's why we get meta product. So remember it. How do you remember the which groups are meta directing groups? Remember it this way. If any atom or group possess multiple bonds, this is nitro group, okay, NO2, nitro group. This is aldehyde group. This is ketone group. This is carboxylic acid group. See, this is attached to the ring, okay, nitrogen here attached to the ring, carbon attached to the ring, and they get multiple bonds. That's why they attract electron like this. Acid chloride group, this is acid chloride. Acid amide group, okay, these are all examples of meta directing groups. Nitro groups, similarly cyano groups, these are all examples of meta directing group. Nitro group, aldehyde group, because they possess multiple bonds. This carbon is attached to the ring also, double or triple bond called multiple bond, and they attract electron from benzene. That's why in benzene ortho and para position becomes positive charge, so meta has little bit more electronegative. That's why incoming electrophile gets attached to the meta. So this type of groups are called meta directing groups, and remember it, meta directing groups deactivate the ring. So remember it, they all deactivate the ring, okay, they all deactivate the ring. So I think you understand it. Now the next question. So remember it, if any atom or group is attached to the ring, contains only sigma bond or single bond, it is treated as orthopara directing group, and if it contains multiple bond, double or triple bond, it is treated as meta directing group. So the question is, which gives meta substituted product by electrophilic substitution reaction? Four options are given. See the option. Number A, A, B, C, D. Everyone undergoes electrophilic substitution reaction. But which of the following single option gives meta substituted product by electrophilic substitution reaction? Can you tell me which of the following gives meta substituted product by electrophilic substitution reaction? This carbon is attached sigma bond, only sigma bond, oxygen, sigma bonds, and you know that if the atoms or groups which is attached with the benzene contains only sigma bond, it has orthopara directing natures. Everywhere there is orthopara, but the only one option where you get meta directing product, and the answer is B. Explanation. What is explanation? If we consider the structure, as the carbon is attached to 3 fluorine atoms, and fluorine has highly electronegative natures, that's why this group, trifluoromethyl group, attracts electron from the ring. So in the ring, positive charge density developed at ortho and para position, that's why the ring is deactivated and it gives meta product. The ring is deactivated and we get meta product. Very important questions. It's a very important question, remember it. It's a very important questions, and whenever any atom or group is introduced on benzene ring, that is always example of electrophilic substitution reaction. In my next video, I will upload electrophilic substitution reactions. There are lots of reactions are there. What are the examples of electrophilic substitution reactions? So I request you, please do watch all my videos and subscribe my channel so that new conceptual questions will reach to you.